Well, again, AP Physics 1. So there's a lot that we're going to cover in this video. Firstly, I want to introduce you to this device here, which is called a motion sensor. You might have used one of these things in maybe PCB2 or some previous science class. But it's a device that can be connected to your computer, and it can measure things like the position of objects away from the sensor, the velocity of objects relative to the sensor, and even the acceleration of objects. So there's a little piece here which can unfold so that you can, let's say, stick this on a tabletop and have an object move back and forth, closer to and further away from the sensor. I want to just briefly remind you or explain to you for the first time, if you're not familiar with this, how this thing actually works. Okay, so how does the motion sensor work? Well, the sensor I have is green here, so I'll draw this in green. The sensor looks something like this, and it's got a little grating over here. And maybe there's an object. Maybe this person here is the object, which is located some distance away from the sensor. So it's actually using sound pulses. What this does is it sends out a little sound pulse, which travels to the object, reflects off the object, and travels back to the sensor again. So every sensor works like this in some ways. Something has to travel from the object that's being sensed to the sensor. Just like when you see something, a light is bouncing off of an object and traveling to your eye, and then you see the object. Or when you hear something, sound is coming from an object or bouncing off an object and going to your auditory detector that you call the ear. And then you hear the sound of the object that made the noise or off of which the noise reflected. So the motion sensor creates this pulse of sound for the purpose of having that pulse of sound bounce off of an object so that the motion detector can then receive that pulse of sound and determine things about the object off of which that pulse reflected. Okay, so how does this thing work? What does it actually measure? Well, let me anthropomorphize here a little bit. If the detector could speak, it would say the following. It would say, I measure delta t for a round trip. What the detector does is it sends out the pulse of sound, which travels away, and then it starts an internal timer. And that internal timer keeps track of how much time it takes between the pulse being sent out and the pulse returning to the motion sensor. So that's what it measures. It measures delta t, the time interval for the round trip between the pulse being sent out and the pulse returning. What the motion detector then calculates is this thing, the distance away from the sensor where the object is located. So how does it do this? Maybe you want to pause the video for a second and think about that. How does the motion detector use the round trip time for a pulse of sound to calculate the distance away from the detector where that object is located? Pause the video now and think about that. Okay. Did you pause it? Only you know for sure. Well, hopefully you appreciate the fact that the distance that the sound pulse travels is related to the time it takes for the sound pulse to travel one round trip. You probably remember from previous science courses that distance equals speed times delta t, or a time interval. And so the distance that one of these pulses of sound travels is 2 little d, where little d is the distance between the detector and the person. Because the sound pulse has to travel a distance little d to get to the person, and then another distance little d to return. And that round trip distance of 2 little d is going to equal the speed of sound, s sound, times the time interval measured by the detector for the entire round trip to be completed. So in this amount of time, delta t round trip, the sound pulse travels the round trip distance, 2d, at the speed of sound. Therefore, the detector, which is hooked up to a computer, can just divide each side of this equation internally, so to speak, by 2, and we get that the distance from the detector to the person is the speed of sound times the round trip time divided by 2. The software that interacts with this detector simply multiplies the speed of sound, which the software knows about. The software has been programmed to know that at room temperature and atmospheric pressure, sound travels at roughly 340 meters per second or so. So it has that number. It measures the round trip time interval. So it multiplies the speed of sound, which it knows, by the round trip time interval, which it measures. It divides by 2, and presto, the machine knows how far away from it the object is located. And this is happening many times a second. The default setting on one of these motion detectors is 20 pulses being sent out a second. So it sends out a pulse, the pulse reflects, comes back, it measures the round trip time, calculates how far away the object is, then it sends out another pulse and does it again, and another pulse and does it again. It's taking 20 distance measurements to the object per second. And therefore, as the object moves around closer to and further away from the detector, 20 times a second, the detector is freshly calculating how far away the object is located. All right, once the detector knows where the object is at each 20th of a second interval, it measures the position, the distance away that the object is located. It can calculate, well, where was the object during the last measurement, and where is the object for the current measurement, and it can figure out what the object's velocity needed to be to move from one place to another. Then it can use the velocity values that it calculates and say, all right, what was the velocity at the previous measurement? What's the velocity for the current measurement? And it can figure out the rate at which the velocity changed between the two measurements and calculate the acceleration of the object. So although the detector most directly calculates just what is the round trip time for a pulse, it can use that to calculate position and velocity and acceleration as well. And the most useful thing about this detector is it can plot for you. It can plot the position, velocity, and acceleration of an object as a function of time. And so you can get a nice graphical representation of these 3 kinematic variables versus time: position, velocity, and acceleration. I want to show you, well, talk to you about what this might look like. When you return to school, you'll be doing a lab pretty early on using this motion detector or a similar one. And I want us to talk about what these graphs might look like. So I have a whole bunch of graphs set up for our use over here. Now you might ask, well, what are you going to do with these graphs, Mr. Frankel? I'll show you. The top graph, we're going to plot position, or x, versus time. The next graph, we're going to plot velocity versus time. And the final graph, we're going to plot acceleration versus time. One thing I should tell you about the detector is it kind of has a built-in x-axis. So the detector, it's facing to the right, the detector, and it considers the positive x direction to be the direction away from the detector. So it considers itself to be x equals 0, and it considers all these positions here, 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 and here to be positive x coordinates. So when the detector renders a graph of, let's say, position versus time, The positions will always be positive, right? Like the object off of which these sound pulses are going to reflect must be in front of the detector for the detector to work properly. So it's only going to register positive positions. And interestingly, it'll actually never register a position of 0 because if the object is directly on top of the detector, which is where the detector considers x equals 0 to be, the detector just doesn't work properly. All right, so let's think about what some graphs might look like. Maybe for this first set of graphs, we have the following. Maybe we have a little person moving at 5 meters per second to the right. So the velocity of this person is 5 meters per second to the right. And let's say the acceleration equals 0. So the person is not accelerating. All right, so you should just imagine that little person running to the right at a constant velocity. There is no rate of change of velocity. There is no acceleration. Let's think about what these graphs might look like now. So for the acceleration graph, this is really simple. The acceleration value is just 0. Therefore, the acceleration graph is going to look like a flat line at acceleration equals 0. As time goes on, the acceleration has a value of 0 meters per second squared. The velocity graph. Well, in my story here, the person is running to the right at a constant 5 meters per second. That means their velocity is not changing over time, but rather their velocity has a constant value of 5 meters per second, which is not changing over time. Take a moment to appreciate that graph. As time goes on, the velocity value is not rising or falling, it's just staying constant. And finally, the position graph over here, well, as the person runs to the right, their x-coordinate is going to get more and more positive. I mentioned just a few moments ago that the x-coordinate can't ever be 0 because that would mean the object is on the detector itself, and then the detector will malfunction. And the x-coordinate can't be negative because that would mean the object is behind the detector and the detector would not function. So we must start with a positive x-coordinate, and the x-coordinate has to increase over time as this little person zips off to the right. Now, there's a couple of things to point out here. First of all, I intentionally drew that position versus time graph as looking linear. And that's because if I were to use the detector to capture the motion of this constant velocity object, the position versus time graph indeed would be linear. It turns out, you might remember this from a previous science course, but when I say the velocity is like the rate at which the position changes, it's the rate of change of the position, that corresponds to the slope of a position versus time graph. So the starting position here, I'll just call, let's see, I'll call this maybe 2 meters. Maybe the object started at 2 meters in front of the detector. But the slope of this thing is 5 meters per second. The slope of a graph of position versus time is the rate at which the position changes with respect to time, which is just the velocity of the object in terms of the language of kinematics. So the position goes up by 5 meters for each 1 second of time that goes by, and the slope over here is therefore 5 meters per second. Okay, let's think of another scenario. So how about this time the person is moving to the left with a speed of 5 meters per second, and again, the acceleration 0. All right, in this situation, again, the velocity is constant, so there is no acceleration. Oh, I better label my axes here. So this is acceleration, velocity, position. All right. And the acceleration is 0 again. The velocity isn't changing. But now the person is running to the left. So their velocity has a constant value of -5 meters per second. And the velocity does not change over time. It flatlines at -5 meters per second. How about the position? Well, the person must start at some positive position. Just like before, I'll imagine the person starts at x equals 2 meters. But as they run to the left, their positive position is getting less and less positive. After all, they're running closer to the detector, closer to x equals 0. So their position has to drop towards 0 over time. Now, it'll never actually hit 0 in this case, because again, if the person were at x equals 0, it would be located where the detector is located, and things will go wrong before then. But essentially, the slope over here will be -5 meters per second, because the slope of a position versus time graph is just the velocity of the object. I should be careful and label my t-axis here as well. Just plug my laptop in. Coordinates. So we have two basic examples here of an object moving at constant velocity, right? The first set of graphs represents constant velocity for, that's weird, that's not writing so smoothly. The first set of graphs represents constant velocity. That means 0 acceleration for an object moving to the right at 5 meters per second. And then the second set of graphs here represents the motion of an object that is moving to the left at a constant 5 meters per second to the left. So the velocity is considered to be a negative value. Okay, so running to the right or running to the left at constant velocity is one thing. It's easy because the acceleration is 0, the velocity values flatline, and the position graphs are linear. They simply have a slope equal to whatever the velocity value is. What if the object is accelerating, though? What if we have an object that is accelerating? So I'm going to zoom in a bit over here. I think I produced too many sets of axes, but that's okay. So let's consider the following situation. Let's consider that we have, for instance, a little inclined plane over here, a little ramp. Okay, so we have a little ramp, and looking at this ramp, I'm going to put my motion detector on top of the ramp like this. And I'm going to have my motion detector look down the ramp. So the x-axis always points away from the motion detector. Whoop, I don't want to do that. I want to pick the whole thing up. Okay, how do I do that? Yes, maybe like this. No, okay. This is the new Zoom whiteboard, and I don't like it. Yeah, how do I move you? Not like this. Okay, getting closer. Oh, well, good enough for now. All right, the x-axis points down. The origin of the coordinate system is going to be located right where the motion detector itself is located. So this is x equals 0. And I'm imagining that I allow some object, like a little cart, for instance, to roll down the ramp. So the initial velocity of this cart is going to be 0. I'm going to allow the cart to start at rest, and I'm going to let it go down the ramp. And as you might imagine, it's going to speed up as it rushes down the ramp in the positive x direction. All right, so what are those graphs going to actually look like? Well, I want to show you the data that I've collected. I ran this experiment. I set up a little ramp. I have the motion detector up here. I let the cart go down, and I took this data. So let's see what this looks like. All right, so what you're looking at here is the acceleration data. All right, right now you're looking at the acceleration versus time. And when you look at this, you might say, oh, the acceleration is like changing in this kind of chaotic way. And it's true that the acceleration of the cart is changing, but is it really changing that much? Notice the vertical axis here where the acceleration is being measured. It varies. First of all, the axis doesn't start at 0, the vertical axis. That should raise some suspicion. Second of all, the axis only goes from 0.1 meters per second squared to 0.2 meters per second squared. So to get a better idea of just how much or little the acceleration is actually varying, I'm going to click on the graph. And I'm going to go to axis options. And I'm going to change what the appearance of this graph is by changing this from negative 0.7 meters per second squared to positive 0.7 meters per second squared. Okay. And the acceleration has that is so weird. That's weird. I have negative values on top and positive values on the bottom. So something's wrong with that. The top should be positive 0.7 and then bottom should be negative 0.7. That's good. I should always have more negative or less positive numbers further down the axis here. So you can see that the acceleration is actually positive. The acceleration is positive, and although it varies a little, it looks to me like it's pretty much flatlining. That tells me that when I release this cart and let it roll down the hill, the rate at which its velocity changed, also known as its acceleration, was pretty much a constant value. In this case, the cart sped up by a constant number of meters per second. Now, we can figure out what that value is. I can highlight this graph over here, and there's an option to analyze, and I'll click on statistics, and it's giving me this little statistics box where it says the mean is 0.15. All right, 0.15. So the mean value of the acceleration is 0.15 meters per second squared. Yes, the acceleration is a little above that and a little below that, but on average, the mean acceleration is 0.15 meters per second squared. So let's go back to the whiteboard over here. This is the first time I am using this new Zoom. I'm repeating myself, but let's see. Let's go back to the whiteboard. It's loading. Okay. And I guess I don't need all this extra stuff here, so I'm going to delete this. Okay. And these 3 graphs will be our 3 graphs for the situation in which the cart is rolling down. In fact, I can move this here so we kind of remember what's going on, and I'll zoom back in again. Okay. So just like last time, we're plotting position versus time. velocity versus time, and acceleration versus time. And we saw that the acceleration of this object has a constant value of about 0.15 meters per second squared. So I'm going to plot that on the appropriate axis here. Okay, the acceleration is roughly 0.15 meters per second squared. I'll write this as 0.15 meters per second squared. And it's pretty much a flat line, constant acceleration value. That means as this cart was going down, its velocity was changing, increasing in this case by at a constant rate. All right, now what about the velocity? You should think about what the velocity graph might look like. The acceleration is the rate at which the velocity changes, right? And so if the acceleration has a constant numerical value of 0.15 meters per second squared, think about what the velocity versus time graph must look like. Let's see if you are right. Go back to the software here. The software is called Logger Pro, by the way. And I'm going to reveal the velocity graph. All right. The velocity graph looks pretty linear. Is it perfectly linear? No, because the acceleration is not perfectly constant at 0.15 meters per second squared. That's just the average. But the velocity graph is pretty linear looking. And I'm going to highlight kind of a section of the velocity graph, and I'm going to go to Analyze Linear Fit. And what this is giving me is the equation of the line here that best represents this pretty linear looking velocity data. So notice here, the slope of this line is 0.1492 meters per second. That should jump out at you. That's almost 0.15 meters per second, otherwise known as meters per second squared. So the slope of this graph looks like it's the acceleration value. It even has the same units as acceleration. There is a vertical intercept of 0.207. It's about 0.21 meters per second. And that tells me the vertical intercept is corresponding to like, well, what was the velocity at t equals 0, the initial moment? I claim that the cart was released from rest, but I guess the cart actually was moving a little bit. It was already moving down the track in the positive x direction. So this velocity versus time graph doesn't go through the origin of the actual axes on the graph, but there's a slight positive vertical intercept over here. I am now going to transfer this information over to our whiteboard. Taking a moment to load. Sorry about that. Okay, so the velocity versus time graph is pretty linear looking. And it looks something like this. Okay, the vertical intercept is about 0.21 meters per second. And the slope of this thing, the slope is approximately 0.15 meters per second squared. Another way to appreciate where these units are coming from is when I divide a change in velocity measured in meters per second by a change in time measured in seconds, the units of that slope are meters per second over seconds. So they are indeed the units of acceleration. Okay, and the equation here is as follows. The velocity is equal to 0 0.21 meters per second plus 0.15 meters per second squared times t. So in like normal geometry class or whatever, or algebra class, this would be like the vertical intercept b. This would be the slope m. This t is taking place of what you usually call x on the x-axis, and this v is taking the place of what you usually call y on the y-axis. So it looks like a line, y equals mx plus b, except there's a physical meaning to these different things. You have the intercept, the vertical intercept, which is a number of meters per second. It's an initial velocity of some sort. It is the initial velocity of the cart. And the slope has a physical meaning too. The slope is the acceleration value. In fact, I think it might be useful to write this down in the most general way possible. It looks like the velocity, which I'll call the final velocity. It's the velocity at some time t that you plug in. The final velocity looks like it's some initial velocity value. So initial velocity value, I'll correct this. The initial velocity, according to the data, is 0.21 meters per second. The cart is already moving down at that very first moment. Plus the acceleration, which is 0.15 meters per second squared times time. I'm going to box that. That's an equation. The final velocity of the object is just equal to the initial velocity of the object plus the acceleration, which is the rate at which the velocity was changing, times how much time has elapsed between that initial moment and the final moment. All right, we'll return to a discussion of that shortly, but let's take a look at what the position graph looks like. All right, we see that the acceleration is a constant positive value, so the velocity versus time graph has a constant positive slope. And now let's take a look at the position versus time graph. So the position versus time graph is the most complicated of all three. If you take a look at it, you can probably sense that it's not actually a linear plot. I mean, if you squint your eyes, sure, you might say, oh, that looks pretty linear, but let me hit this auto scale button, this little A over here. That didn't make it look any less linear, but it's actually not linear. If I were to take data for more time, you would see that this graph curves away from what a straight line would look like. The next simplest curve fit that we could try to fit onto this data after we realize that, yeah, linear fit doesn't look like it's so great. The velocity graph looks a lot more linear than the position graph. It would be a quadratic or some kind of parabolic curve fit. So I'm going to highlight this, go to Analyze, Curve Fit, and this time I'm going to go to a quadratic curve fit. Try fit. I'm going to hit OK, and I have some data here. Alrighty, so can we make sense of this? Sure we can. So it looks like the generic formula, which they're giving me here, is x equals at squared plus bt plus c. That is the standard form of a parabola if x is what I'm plotting on the vertical axis and t, time, is what I'm plotting on the horizontal axis. And it's giving me some numerical values for A, for B, and for C. I'm going to write these down on a piece of paper for myself because the next thing I want to do is jump over to the whiteboard again and record all this down near this graph. So it looks like it's telling me that x is 0.075 roughly times t squared plus b, which is 0.2, I'll round, 0.21 times t plus c, which is 0.18. All right. Let's go back to the whiteboard. How do I do this? Okay. Okay, so the graph looks something like this. It's kind of quadratic looking. I mean, it is parabolic looking. Now, how do I know it's a parabola? I don't. Really looking at those coefficients, those A, B, and C constants, if I can make physical sense of them, that would give me confidence that a quadratic fit is the appropriate fit here. So let me write down the equation that the computer, the Logger Pro software gave me. I'm going to write this down in reverse order. 0.18 plus 0.21 t plus 0.075 t squared. My pen is not too accurate. I'll zoom in a bit. All right, let's try to make sense of these things. So at t equals 0, if I set t equal to 0, what I'm getting is the position, the x coordinate of the object away from the detector at t equals 0. And that must correspond to the vertical intercept, right? When time equals 0, how far up do we go in terms of the x coordinate, the position of the object? Apparently, that's 0.18 meters. So the initial position of the object is 0.18 meters. There must be units on these things. That constant must be 0.18 meters. After all, the position is measured in meters. Every term on the right-hand side that I'm adding together must also have units of meters for that to be consistent. The next thing is, so this is the initial position. I'll call this x initial. The next thing to note is that the linear term has a coefficient of 0.21. That looks familiar. Hopefully it looks familiar to you. 0.21 meters per second was the initial velocity of the object. So the units of this actually must be meters per second, because when I multiply a coefficient with units of meters per second by a time in seconds, the seconds cancel out and the whole thing has units of meters, again, as it must. Each term on the right-hand side of this expression must have units of meters or they couldn't be added together. So it looks like that is the initial velocity. It looks like the initial velocity is important in determining what the position will be in the future. And finally, this last term, 0.075 times t squared, the quadratic term. Time is measured in seconds, so time squared is measured in seconds squared. But this whole thing, this whole term must have units of meters. Hence, I know this coefficient, 0.075, must have units of meters per second squared, so that when I multiply it by a time squared, I just get meters as my unit. And that 0.075 has units of acceleration, although it's not the acceleration. The acceleration of the object is 0.15 meters per second squared. This is very close to that, though, or very closely related. This looks like it's 1/2 the acceleration. So what is the position of this object at any time t that we plug in? Well, the position is dependent on the initial position, the initial velocity, And the acceleration, although the acceleration times 1/2 is what actually shows up in the formula. Let me write this formula down. X final, the final position, is equal to the initial position plus the initial velocity times time plus 1/2 the acceleration times time squared. And I'm going to box that. That's another really good formula. If I know the initial position, the initial velocity, and the acceleration, any time I plug in here will tell me what the final position is. Will allow me to calculate that, I should say. All right, so what is the slope relationship here? I'm going to make another video where I dive into the details of this, but just to point something out to you, notice how the velocity value gets more and more positive over time. The velocity value getting more positive over time means the rate at which the position is changing is getting more and more positive. But if the rate at which the position is changing is getting more and more positive, the position should be shooting up more and more rapidly. In fact, it is. The slope of this parabola is not a constant. It's not constant because the parabola is not a line. And I can see that the parabola is arcing up, sloping up more and more dramatically over time. It means as time goes on, it takes less and less time for the next huge, and increasingly huge, I should say, jump in position to be achieved. So although the acceleration being constant leads to the velocity increasing at a constant rate, constant slope, the velocity increasing leads to the position increasing at an increasing rate. Say that one more time. The velocity is increasing. The velocity is the rate at which the position changes. Therefore, the position is increasing, but it's not increasing at a constant rate. It's increasing at an increasingly large rate. The slope of the position versus time graph itself goes up over time. Okay. Now, I'm going to write these two equations down because they are really important. They're going to appear over and over again. There are actually 3 equations that we're going to be using in this unit, but I'm going to call these the constant acceleration kinematics formulas. All right. If the acceleration of the object is constant, as it is in the case of a cart rolling down a inclined track, then there are relationships between, there are equations we could use to compute the future position and the future final velocity of the object. So the final position is equal to the initial position plus the initial velocity times time plus 1/2 the acceleration times time squared. And the final velocity is just equal to the initial velocity plus the acceleration, which is the rate at which velocity changes, times time. I'm going to call this kinematics equation 1, and I'll refer to that throughout the course as either the position formula or kinematics equation 1. And I'm going to call this equation 2. Throughout the course, I will refer to this equation as the velocity formula or kinematics equation 2. I have to stress that these equations, these formulas, only apply to objects which have a constant value acceleration. Happily, most of the problems we deal with in this course will be problems where the acceleration of the object is constant. And so you can use these formulas to plug in a time and compute the future position and velocity. Okay, this video ran a little longer than I expected due to me fumbling around with the new Zoom interface. So I will sign off now and post another video when I have the energy and you have the bandwidth to appreciate it. If you want, you can turn your attention right now to the graphing kinematics quantities homework. And if you struggle with that, just remember sometime in July, I will be posting the solutions so you can see how reasonable your hypotheses were as to what these graphs should look like. But stay tuned for more.